Chapter 13 Principles of Unit Protection. Protective Relay Systems. The basic function of a protection is to detect faults and to clear them as soon as possible. It is also important that in the process, the minimum amount of equipment should be disconnected. The ability of protection, i.e., relays and circuit breakers, to accomplish the latter requirement is referred to as selectivity. Speed and selectivity may be considered technically as figures of merit for a protection scheme. In general, however greater the speed and/or selectivity, the greater is the cost. Hence, the degree of speed or selectivity in any scheme is not purely a technical matter. It is also an economic one. Main or unit protection. The graded overcurrent systems described earlier do not meet the protection requirements of a power system. As seen in Chapter 10, the grading is not possible to be achieved in a long and thin networks, and also it can be noticed that grading of settings may lead to longer tripping times closer to the sources, which are not always desired. These problems have given way to the concept of unit protection, where the circuits are divided into discrete sections without reference to the other sections. Ideally, to realize complete selectivity of protection, the power system is divided into discrete zones. Each zone is provided with relays and circuit breakers to allow for the detection and isolation of its own internal faults. This ideal selective zoning is illustrated in Figure 13.1. The protection used in this manner, essentially for internal faults in a particular zone, is referred to as main or unit protection. Backup protection. It is necessary to provide additional protection to ensure isolation of the fault. When the main protection fails to function correctly, this additional protection is referred to as backup protection. For example, referring to the above figure, assume that a fault has occurred on the feeder and that the breaker at A fails to open. To clear this fault, the circuits which are able to feed current to the fault through the stock breaker A must be open. The fault is outside the zones of the main protection and can only be cleared by the separate backup protection. Backup protection must be time delayed to allow for selective isolation of the fault by the main or unit protection. Methods of obtaining selectivity. The most positive and effective method of obtaining selectivity is the use of differential protection. For the less important installations, selectivity may be obtained at the expense of speed of operation with time-graded protection. The principle of unit protection was initially established by Merz and Price, who were the creators of fundamental differential protection scheme. These systems basically employ the direction of current rather than their actual values, protecting a particular zone by means of detecting the circulating currents through pilot wires and relays. The basic principles of these well-known forms of protection will now be considered. Differential protection, as its name applies, compares the currents entering and leaving the protected zone and operates when the differential between these current exceeds a predetermined magnitude. This type of protection can be divided into two types, namely balanced current and balanced voltage. Balanced circulating current system. The, princi- the principle is shown in figure 13.2. The CTs are connected in a series and the secondary current circulates between them. The relay is connected across the midpoint, thus the voltage across the relay is theoretically nil. Therefore, no current through the relay and hence no operation for any faults outside the protected zone. Similarly, under normal conditions, the currents leaving zone A and B are equal, making the relay to be inactive by the current balance. Under internal fault conditions between the cities at end A and B, relay operates. This basically due to the direction of current reversing at end B making the fault. Current to flow from B to A instead of the normal A to B. In the earlier figure 13.3. The current transformers are assumed identical and are assumed to share the burden equally between the two ends. However, it is not always possible to have identical current transformers and to have the relay at a location equidistant from the two end cities. It is normal practice to add a resistor in series with relay to balance the unbalance created by the unequal nature of burden between the two end circuits. This resistor is named as stabilizing resistance. Balanced voltage system. As the name it implies, it is necessary to create a balanced voltage across the relays in ends A and end B under healthy and out of zone fault conditions. In this arrangement, the cities are connected to oppose each other in figure 13.4. Voltages produced by the secondary currents are equal and opposite. Thus, no current flow in the pilots or relays, hence stable on true fault conditions. Under internal fault condition, relays will operate, as you can see in figure 13.5. The balance or circulating current systems are invariably used for generator, transformer, and switchgear main protection, where it is conveniently to readily access the midpoint of the pilots. This is because both sets of CDs are mounted in the same substation and a single relay is used to detect the fault condition within the protected zone. On the other hand, balanced voltage systems are used mainly on feeder protection, where the CTs are mounted in different substations, which are some distance apart. As these are two relays involved, one at each end, they can each be mounted in their respective substation, although similar. The various forms of differential protection differ considerably in detail. The differences are concerned with the precautions taken to ensure stability, to ensure that the protection does not operate incorrectly for a true fault. The spill current in the differential relay due to the various source of errors is dependent on the magnitude of the throughout current. Hence, it is necessary to consider the setting of the differential relay to be more than or proportional to the worst spill currently likely to occur under true fault conditions. Because of the wide range of fault current magnitudes, it is not always satisfactory to make the relay insensitive to lower spill current values. This problem had been overcome by adjusting the operating level of the relay according to the total amount of the fault current. This was done originally by providing a restraining winding or electromagnet which carries the total fault current, while an operating electromagnet was allowed to carry only the differential current. This principle of bias is applied to circulating current protection to ensure proper operation under all fault conditions. If the two zone boundary currents are I1 and I2, then operating quantity is K1 times I1 minus I2. Biasing quantity is K2 times I1 plus I2. Suitable choice of constants K1 and K2 ensures the stability for external faults currents despite measurement errors, while still ensuring stability under internal fault conditions. Machine differential protection. The balanced circulating current principle is normally used. The bias feature is introduced to ensure stability beside possible small differences in the performance of the two nominally balanced sets of current transformers. Sensitivity of this protection is normally of the order of 10%, which means that the protection will operate when the differential current is greater than 10% of the normal full load. Without bias for true fault current of 10 times full load, the protection would operate if the spill or differential current exceeded 10% of full load or 1% of the true fault current. To avoid necessity of matching current transformers to this degree of accuracy, the protection is biased with throughout current. Transformer differential protection. A typical transformer differential protection system also adopts the circulating current principle. The first point to notice is that the CTs on one side are connected in delta, whilst they are connected in star on the other. This has been done for two reasons. One, to correct for the phase shift through the transformer in order to obtain cophasal currents at the relay. Two, to prevent the relay from operating incorrectly for an external fault on the side of the power transformer where the windings are connected in star with the neutral earthed. True current bias is necessary on these relays not only for the inherent imbalances of the cities, but also to take care of any voltage tappings on the transformer provided by the tap changer. For example, a transformer having a nominal ratio of 132 over 40 kilovolts having a tap change range of plus 15 to minus 5% on the 40 kilovolt side would have the current transformer ratio selected to be balanced at the mid tap, namely 132 over 42 kilovolts. Switchgear differential protection. In switchgear differential protection, all the currents entering and leaving the protected zone are added if the resultant is zero. Then the bus bars are healthy. However, if the current exceeded the chosen setting, the protection will operate and trip all associated circuit breakers. The stability of this type of protection is obviously of vital importance since an incorrect operation could result, for example, in the shutdown of power station. On account of the large number of circuits involved, all carrying different currents, stability is also more difficult problem than with machine. For transformer differential protection, a number of different schemes are used for this protection, normally referred to as bus zone protection. Feeder pilot wire protection. Pilot wire protection is similar to differential protection in that it normally compares to the current entering the circuit at the one end with current leaving at the other end. Its field of application is the protection of power cables and short transmission lines. For these circuits, the distance between the current transformer at 2 ends of the protected zone is too great for the circulating current differential protection, the type described previously for machines and transformers. The pilot wire provides a communicating channel for conveying the information relative to conditions at one end of the feeder to protective relays at the other end of the feeder and vice versa. These relays or group of relays at the two ends are able to make a comparison between local and remote conditions, and thus determine if there is an internal fault. Each relay normally trips only its associated circuit breaker. There are many different types of pilot wire protection schemes, but the most commonly used are of the opposing voltage type, an example of which is illustrated in chapter 14. Time taken to clear faults. With the inherently selective forms of protection, apart from ensuring that the relays do not operate incorrectly due to initial transients, no time delay is necessary. Operating times for the protection, excluding the breaker, tripping or clearing, time are generally of the following order. Machine differential is a few cycles. Transformer differential is 10 cycles. Switchgear or busbar differential, 4 cycles, and feeder differential also a few cycles. These operating times are practically independent of the magnitude of fault current. Recommended unit protection systems. Cable feeders. For cable feeders, you will use pilot wire differential. Transformer, HV balance restricted earth fault. For high voltage, high set instantaneous overcurrent, and low voltage restricted air fault or butchels. Bus bars, medium or low impedance schemes for strategic bus bars, including bus bars operating on closed rings. Bus bar blocking schemes for regional networks. Unit protection should be used where possible throughout the network. Remove the inverse time. Relays IDMT from the front line. IDMT must be retained as backup only to cover for a failure of the main protection. Advantages of a unit protection. Fast and selective. Unit protection is fast and selective. It will only trip the faulty item of plant, thereby ensuring the elimination of any network disruptions. Easy to set. Unit protection is easy to set and once installed, very rarely it requires changing, as it is independent of whatever happens elsewhere in the system. No time constraints. Time constraints imposed by the supply authorities do not become a major problem anymore. They only need consideration when setting up the backup inverse time. Maximum operating flexibility. The system can be operated in any switching configuration without fear of a loss of discrimination. Better continuity of supply. In many application rings can be run close, so that switching would not be necessary to restore loads, resulting in better continuity of supply. Future expansion relatively easy. Any future expansion that may require another in-feed point that can be handled with relative ease without any changing to the existing protection.
Chapter 14 Feeder Protection, Cable Feeders, and Overhead Lines. Two commercially available systems have been chosen as typical examples to illustrate the concept. However, there are other similar products on the market using essentially the same technology. So translay, so it's like a combination of transformer and relay. Once the feed is healthy, the line cities at each end carry equal currents. Equal and opposite voltages are induced in the secondary windings 12 and 12A, and no current flows in the pilot. No magnetic flux is set up in the bottom magnet 16 and 16A, so the relays do not operate. Under heavy through fault conditions, there may be a small circulating current due to line CT mismatch. A restraint torque is produced by bias loop 18, which also stabilizes the relay against pilot capacitance current. A fault fed from one end causes current to circulate in the pilots, and the relay at the end will operate to trip. A fault fed from both ends will cause a current reversal in the remote CTs, making the circulating current additive so that both ends operate trip. So, as you can recall, no current flows in the pilots, but due to fault from one end or both, a current will flow or circulate in the pilots, causing the relay to operate trip. So ito yung second way, soul core protection. So ito yung schematic diagram ng soul core R protective system. So, yan pala nakakalula na. So, gawin natin mas simple. So, ito basic circuit of soul core R protection. So, yan. So, ito para itong rectifiers. Pero, imagine lang natin to as diodes para maging simple. So, operating coils, ayan yung nag-ooperate sa relays para mag-trip. So, RP, ibig sabihin niya resistance ng pilot wires. Soul core unit protection is used where solid metallic pilot wires are available. Optional equipment includes pilot wire supervision and injection intertripping systems. The system is a differential protection system and is available as SOCOR R and RF. So, kung may interest kayong i-research tong SOCOR protection, mas best na i-research nyo yung differential protection system. Mas itong available sa internet. So, SOCOR R mode, where pilot earth insulation levels are 5 kilovolts or less. Its stability for true faults is the same value as SOCOR RF. So SOCOR RF mode, used in newer systems with either 5 or 15 kilovolt insulation, gives faster clearance times for internal faults. So meaning lang no, itong SOCOR RF mas newer version for 5 or 15 kilovolts insulation, pero kung 5 kilovolts or less, mas maganda gamitin SOCOR R mode. The standard relay has a pilot circuit to earth withstand of 5 kilovolts, and interposing transformers are available to cater for circumstances when a 15 kilovolt pilot insulation level is required. Solar equipment will trip both ends of a faulty feeder even if current is fed from one end only. Solcor R and RF relays are designed to use telephone-type pilot cables having a loop resistance of up to 2 kilo ohms and a maximum capacitance between cores of 2.5 microfarad. The relays incorporate diodes which act as switches and permit the use of a single pilot for two-way signaling using a system of time-sharing switch at the power frequency. Normally, only two pilot wires are used for interconnecting the relays at two ends of the feeder. For this reason, summation transformers are incorporated in the protection. Because of the summation transformer, the sensitivity of the protection is dependent upon the phases that are involved in short circuit. Typical figures for sensitivity are as follows later. So again, ito yung basic circuit diagram ng SOCOR R protection. So kung under external fault conditions or outside siya ng SOCOR protection system yung fault natin, either from right side or left side or kung anong rectifier ang nag-short, ganito ang behavior ng voltage niya throughout the system. So sabihin natin sa right side yung external fault or yung M2 yung nag-short na rectifier. So ganito yung behavior ng voltage throughout the cycle. So positive dito, Pagpunta dito, neutral. At pagpunta dito, negative na. So, nadaanan ng negative voltage to. Kaya man, balik rin natin na dito yung external fault kasi ito yung nag-short na rectifier. So, kung negative hanggang sa mapunta pa rin dito sa RP, negative pa rin siya hanggang sa pagtaas dito, positive na. So, nadaanan pa rin siya ng kuryente sa RP or yung pilot wires. So, ito naman tayo behavior pag internal fault condition or mismong protection system natin ang may fault na. So, during positive half cycle, so, merong voltage na magpapasok direkta sa operating coil or yung coil ng tripping device. So, during negative half cycle na magpabalik naman yung voltage. So, voltage pa rin nadadaan sa pilot wires na magtitrigger ng tripping device. So, itong summation ng transformer. So, pag tingin nyo dito, parang familiar to. So, para itong 3-phase transformer. So, neutral, blue, yellow, red. So, pag tingin nyo dito, familiar siya kasi kamukha siya ng 3-phase vector diagram. So, each line separate siya ng 120 degrees. So, syempre, ano ba yung point of origin? Ayun yung earth or 0 volts or parang ground ito. So, ibig sabihin ito, ground to. Tapos itong tatlo, yung linya. So, ito naman yung type of fault. Saka ito naman yung sensitivity niya o yung fault settings. So, pag sinabing N-tap, dito yon or dito. Tapos pag sinabi ng N1 tap, dito yan or dito. So, pag sinabing red to earth or red to N at red to N1, makikita natin dito yung red to N or red to N1. So, example, pag red to N, 25% sensitivity. Kung red to N1, 18% sensitivity. So, bakit may dalawang category dito? So, as you can recall, 5 kilovolt equipment, pwede itong Solcor R or Solcor RF in lowest settings. Pero pag 15 kilovolt equipment naman, ito para sa Solcor RF naman to. So, red to N in Solcor RF mode is equals to 33% of sensitivity. So, makikita mo dyan yung rating na iba. Blue to N, red to yellow, yellow to blue, red to blue, 3-phase. So, recommended protection of cables and short lines, pilot wire differential protection, Solcor and Translate, etc. Backup inverse indefinite minimum tie block or IDMTL. IDMTL relays not for overload. Cable selected for bolt drop and fault level.
Okay, so now we move on to distance protection. A distance relay, as the name implies, has the ability to detect a fault within a preset distance along a transmission line or power cable from its location. Every power line has a given resistance and reactive per kilometer related to its design and construction. So the total impedance will be a function of its length or distance. A distance relay therefore looks at the current and voltage and compares these two quantities on the basis of Ohm's law. Since the impedance of a transmission line is proportional to its length, for distance measurement, it is appropriate to use a relay capable of measuring the impedance of a lineup to a predetermined point, also called or known as the reach point. The basic principle of a distance protection involves the division of voltage at the relaying point by the measured current. The apparent impedance is so calculated is compared with the reach point impedance. If the measured impedance is less than the reach point impedance, it is assumed that a fault exists between the line. The reach point of a relay is the point along the line impedance locus that is intersected by the boundary characteristic of the relay. Since this is dependent on the ratio of voltage and current and the phase angle between them, it may be plotted on an RX diagram or a resistance to reactance diagram. The low C of the power system impedances, as seen by the relay during faults, power swings and load variations may be plotted on the same diagram, and in this manner, the performance of the relay in the presence of system faults and disturbances may be studied. Here we can see the basic diagram for the basic principle of operation for such a distance relay. Now, this concept can be best appreciated by looking at a pioneer type balanced beam relay shown in this figure. The voltage is fed onto one coil to provide restraining torque, while the current is fed to the other coil to provide operating torque. Now, under healthy conditions, the voltage will be high, while the current will be low at normal load value, thereby balancing the beam and restraining it so that the contacts remain open. Under fault condition, wherein the voltage on this side collapses, and thus the current on this side increases exponentially, it causes this beam to be imbalanced and thus trip or close this circuit, which causes it to be a fault. Now, by changing the ampere turns relationship of the current coil to the voltage coil, the ohmic reach of the relay can be adjusted. A more modern technique for achieving the same result is to use a bridge comparator, as seen in this figure. Tripping characteristics of distance relays. If the relay's operating boundary is plotted on the resistance and reactance diagram, its impedance characteristics is a circle with its center at the origin of the coordinates, and its radius will be the setting or the reach in ohms. Now, the relay will operate for all values less than its settings, i.e., it's all for all points within the circle, within this circle. This is known as a plane impedance relay, and it will be noted that it is non-directional, in that it can operate for faults behind the relaying point. It takes no account of the phase angle between the voltage and current. The limitation can be overcome by a technique known as self-polarization. Additional voltages are fed into the comparator in order to compare the relative phase angles of the voltage and current, so providing the relay a directional feature. This has the effect of moving the circle such that the circumference of the circle now passes through the origin. Angle theta is known as the relay's characteristic angle. This is known as an MHO relay, so called as it appears as a straight line on an admittance diagram. By the use of a further technique of feeding in voltages from the healthy phases into the comparator, this is known as cross-polarization, a reverse movement or offset of the characteristic can be obtained. This is called the offset MHO characteristic. This is the diagram for the offset MHO characteristic, wherein the circle for the working range of the distance relay is shifted. How do we apply this onto a power line? Well, correct coordination of the distance relay is achieved by having an instantaneous directional zone 1 protection and one or two more time delayed zones, zone 2 or zone 3. A transmission line has a resistance and reactance proportional to its length, which also defines its own characteristic angle. It can therefore be represented on a resistance and reactance diagram, as shown below. The application onto a power line for zone 1, the relay characteristic has also been added, from which it will be noted that the reach of the measuring element has been set at approximately 80% of the line length. This underreach setting has been purposely chosen to avoid overreaching into the next line section to ensure sound selectivity for the following reasons. It is not practical to accurately measure the impedance of a transmission line, which would be very long, for example, 100 kilometers. Survey lengths are normally used, and these could have errors up to 10%. Errors are also present in the current and voltage transformers, not to mention the possible transient performance of these items. Manufacturing tolerances on the relay's ability to measure accurately. Application onto a power line for zone 2. To cover the remaining 20% of the line length, a second measuring element can be fitted, set to overreach the line, but it must be time delayed by 0.5 seconds to provide the necessary coordination with downstream relays. This measuring element is known as zone 2. It not only covers the remaining 20% of the line, but also provides a backup for the next line section, should this fail to trip for whatever reason. Zone 3 is a third zone that is invariably added as a starter element. This takes the form of an offset MHO characteristics. This offset provides a closing onto fault feature, as the MHO elements may not operate for this condition due to the complete collapse of voltage for nearby fault. The short backward reach also provides local backup for a busbar fault. This element can also be used for starting a carrier signal to the other end of the line. The zone 3 element also has a very useful function. As a starter, it can be used to switch the zone 1 element to zone 2, which after say 0.5 seconds, thereby saving the installation of a second independent zone 2 measuring element, so reducing its cost. Here we can see the diagram for the 3-zone MHO characteristics. So zone 1 reaches up to 80% of the total length of the line, while zone 2 covers the remaining 20% of the line, and zone 3 acts as a starter or a backup. Now we have the effect of load current. Load current can also be expressed as impedance. Again, by the simple application of Ohm's law, this can be shown on the resistance reactance diagram. As depicted by the shaded area, the angular limits being governed by the power factor of the load, shown here. It's important that when setting distance relays, especially in zone 3, which has the longest reach, its characteristic does not encroach on the load area, as unnecessary tripping will undoubtedly occur. The effects of arc resistance. Resistance of fault arc can also have an impact on the performance of distance relay, as it can be seen on the following resistance reactance diagram. It will be noted that the resistance of the fault arc takes the fault impedance outside the relay stripping characteristics, so it does not detect this condition. Alternatively, it's only picked up by either zone 2 or zone 3, in which case tripping will be unacceptably delayed. The effect of arc resistance is most significant on short lines, where the reach of the relay setting is small. can be a problem if the fault occurs near the end of the reach. High fault arc resistances tend to occur during mid-span flashovers to ground, during a belt fire, or on transmission lines carried on wood poles without earth wires. These problems can usually be overcome by using relays having different shape characteristics, as described here. We also have different shape characteristics. To overcome the problems of load encroachment, as stated before, and arc resistance, distance relays have been developed having different shape tripping characteristics. Some examples of which are as follows: the circular, as given before, the lenticular, the figure of eight, and the trapezoidal. With the advent of modern digital technology, many shapes are now possible to suit a variety of applications. Here we have the lenticular characteristic. We also have the figure of eight characteristic. Of course, finally we have the trapezoidal characteristic. Now, distance protection schemes. Because of the various zones, distance protection is strictly speaking not a pure form of unit protection. However, with the addition of an information link between two ends of the line, it can be made into a very effective unit protection system. The normal method of achieving this is to install a power line carrier signal channel between two ends. The signal is injected into the power line conductors at one end via a capacitor voltage transformer and picked off the other end by a similar device. Line traps are installed at either end to prevent the signal dispersing through all other lines in the network. Other types of communication medium can be used such as copper, fiber optic pilots, or microwave radio. Could be considered if line of sight is available. Here we have the conventional distance scheme. When the signaling equipment is not available, the conventional distance scheme illustrated here is used. However, faults at the end 20% of the line will only be cleared in zone 2 time, namely 0.5 seconds. You can see this is a graph. This is how much time it takes. So for zone 1, it's always first, and for zone 2, it's around 0.5 seconds delayed. And for zone 3, which is the end zone, this is the stepping time / distance characteristics. This symbol represents the fault. Here we also have trip circuit contact logic and trip circuit solid state logic. Now we also have zone 1 extension or overlap. Fast tripping for these portions can be achieved by extending the reach of zone 1 to 120% of the line and cutting it back to 80% reach after tripping before auto-closing the breaker. The logic is shown in the figures here, wherein zone 1 has been extended here, represented by the broken line, and over here goes past zone 2, reaching 120%. Of course, we also have the trip circuit logic, wherein we now have zone 1 extensions here and here. And for the simplified solid state logic, We auto reclose reset zone 1 extension here. For direct transfer trip or the underreaching scheme, when the carrier/signaling is available, the simplest way to speed up a fault clearance at the terminal, which clears an end zone fault in zone 2 time, is to adopt a transfer trip or inter-trip technique, as shown in the figures given the next slides. Here in the figure, we can see the receive relay contact added in parallel. A zone 1 contact is used to send a carrier signal to the remote end to directly trip that breaker via a receive relay. The disadvantage of this scheme is the possibility of undesired tripping by accidental or maloperation of the signaling equipment. Permissive underreach scheme. The direct transfer trip scheme is made more secure by monitoring the received signal with instantaneous zone 2 operation before allowing tripping, as shown in this figure here. So before, the receive relay contact was located here by itself, and now it's monitored by the instantaneous zone 2 operation. And we can see right here the receive relay contact and the time delay on reset. We see the signaling channel send arrangement, and of course, simplified solid state logic for the permissive underreach scheme. The time delayed resetting of the signal received element is required to ensure that the relays on both ends have time to trip when the fault is close to one end. The breaker is one end is opened, instantaneous clearance cannot be achieved for end zone faults near the breaker open terminal. We also have the acceleration scheme. This scheme is similar to the previously stated permissive underreach scheme in its principle of operation, but is applicable only to zone switch distance relays, which share the same measuring elements for zones 1 and 2. So here you can see for the distance/time characteristics, zone 1 and zone 2 are related. So the longer reach of the measuring elements gives better arc resistance coverage, so it is better suited for shorter lines. This scheme is sometimes referred to as a directional comparison scheme. In this scheme, the incoming carrier signal switches the zone 1 reach to zone 2 immediately without waiting for the zone 2 timer or the 0.5 second delay to switch the reach. This accelerates the fault clearance at the remote end. Now we have the permissive overreach scheme. In this scheme, a measuring element at end A is set to overreach beyond the far end of the protected line, typically 120% or more. The same scheme is installed at the other end of B of the line, looking towards end A. This element sends an inter-trip signal to the remote end. It is arranged to trip its own breaker immediately after the signal is received. If no signal is received, it will trip its own breaker after zone 2 time. The longer reach of the measuring elements gives better arc resistance coverage, so it is better suited to short lines. This scheme is sometimes referred to as directional comparison scheme. Now we finally have a blocking scheme. The schemes described above have used signaling channel to transmit tripping instruction normally through the fault. A blocking scheme uses inverse logic, the signal preventing tripping. Signaling is initiated only for external faults, takes place over healthy line sections. Fast fault clearance occurs when no signal is received and the overreaching measuring elements looking into the line operate. The signaling channel is keyed by a reverse looking distance element at zone 3. An ideal blocking scheme shown in this figure right here.